Welcome to our lecture on parasitic arthropoda. Today, we are going to explore a group of tiny, highly specialized organisms that have profoundly shaped human history and global public health. We will understand not just what they are biologically, but how they multiply exponentially and spread deadly diseases, building your understanding completely from the ground up. Let us start by imagining your house is suddenly invaded by tiny, unwanted guests who eat your food and use your home to breed. In the biological world, our bodies are these houses. Unlike internal parasites, such as tapeworms, that live inside the gut, parasitic arthropods are strictly ectoparasites. This means they live exclusively on the outside of our bodies, attaching firmly to our skin, hair, or clothing. Creatures like ticks, mites, fleas, and bedbugs are the ultimate hitchhikers, relying entirely on us for their blood meals and their very survival. Now that we understand what ectoparasites are conceptually, let us look at how they are formally classified in biology. These creatures belong to the massive phylum Arthropoda, which is biologically characterized by having jointed appendages and a tough, hard exoskeleton. In the study of parasitology, we focus specifically on two classes: Insecta, which includes fleas and lice, and Arachnida, which includes ticks and mites. Over millions of years, these organisms have evolved highly specialized mouthparts that are perfectly adapted for piercing tough human skin and efficiently sucking out blood or tissue fluids. Understanding their biology leads us to a crucial question. Why do we study them so closely in medicine? The answer lies in their severe real-world impact. While they cause direct physical damage like blood loss, severe allergic reactions, and intense itching that leads to secondary bacterial infections, their real danger is acting as delivery vehicles. They serve as biological or mechanical vectors for deadly pathogens. Historically, the rat flea transmitted the devastating bubonic plague, and today, ticks spread Lyme disease. By studying them, we can design highly effective control strategies to prevent massive outbreaks. Knowing the severe diseases they carry, we must understand how quickly these biological threats can escalate in a community. When a parasite, like a bedbug, enters a new environment with plenty of hosts, it does not just add a few bugs at a time, it multiplies continuously. To truly grasp this danger, we use mathematical models for exponential population growth. This mathematical tool is absolutely essential for public health officials, allowing them to predict exactly how large an infestation will become over time and determine how urgently a medical intervention is needed. This brings us to the mathematical representation of an infestation. The formula is N of t equals N0 times e to the power of r times t. Conceptually, this equation states that the future population equals the starting population multiplied by a continuously compounding growth factor. N0 is the initial number of parasites that started the infestation. The letter E is Euler's number, representing the base rate of natural continuous growth. The variable r is the intrinsic growth rate, which is daily births minus deaths. If this reproduction rate increases even slightly, the population explodes much faster. Before we move on, let us see this formula in action with a concrete example. Imagine a dorm room with an unnoticed infestation of exactly 5 bedbugs. The growth rate is 0.1 per day, and we want to find the population after 30 days. We substitute our given values into the equation. First, we simplify the exponent by multiplying 0.1 by 30, giving us 3. Evaluating e to the power of 3 gives a compounding factor of about 20. Multiplying this by our initial 5 bugs yields roughly 100 adult bedbugs. This shows how a barely noticeable presence rapidly becomes a severe infestation. Now that we have seen how fast the vectors themselves multiply, let us look at how they actually spread disease. Parasitic arthropods act as vectors, meaning they carry pathogens from one host to another. A successful infection requires 3 biological realities to align. An infected vector must be present, it must bite a human host, and it must successfully transfer the pathogen during that bite. By modeling this mathematically, we can calculate the daily disease transmission risk in a specific area, which helps us quantify the immediate threat of an infected vector population. To calculate this risk, we use a straightforward transmission formula. R equals P times B times S. Conceptually, this equation multiplies the total number of infected vectors by their daily biting rate to find the total number of bites. Then it multiplies that by the probability that a bite actually transmits the disease. P is the infected vector population. B is the average number of times each vector bites a human per day. S is the biological probability of successful transmission. If the vector population P increases, the number of new infections, R, rises directly with it. Let us apply this formula to a real-world scenario. In a rural village, there are 200 rat fleas infected with plague bacteria. Each flea bites a human 0.5 times per day, with a 0.4 probability of transmitting the bacteria. We substitute these values into our equation. First, we multiply 200 fleas by 0.5 bites, telling us there are 100 infectious bites happening every day. We then multiply these 100 bites by the 0.4 chance of transmission. This results in exactly 40 new human plague infections expected every single day. So we have successfully calculated the daily infections. This brings us to a mathematical proof of why vector control is so critical. Let us set up the derivation using our transmission risk equation. R equals P times B times S. Notice that the biological factors, the biting rate of 0.5 and the success rate of 0.4, are relatively low and often fixed by nature. When we multiply them, we get a combined transmission factor of 0.2 per vector. This simplifies our equation to R equals 0.2 times P, showing a direct proportional relationship. Continuing our derivation, this simplified equation, R equals 0.2 times P, reveals a profound physical reality. It shows that the number of new infections scales linearly with the vector population. Even with a low individual biting risk, a massive population of infected arthropods guarantees a rapid disease outbreak. Because R depends directly on P, reducing the vector population through targeted insecticides will directly and proportionally reduce the number of new infections. This mathematically proves why controlling the vector population is the most effective way to stop an epidemic. To visually reinforce what we just proved, let us look at this diagram of the transmission mechanism. You are seeing a magnified cross-section of human skin. Notice the adult tick at the top. Its specialized mouthparts have pierced through the outer epidermis and deep into the dermis to reach the blood vessels in the subcutaneous tissue. Look at the green, rod-shaped pathogens traveling from the tick's salivary gland directly into the host's bloodstream. The inset graph on the right illustrates the result. Once inside, the pathogen load in the host rises exponentially over time, driving the progression of the infection. We have covered a lot of ground today, so let us summarize our key takeaways. First, parasitic arthropods are specialized ectoparasites that rely entirely on host blood for survival. Second, their greatest medical significance is acting as highly efficient vectors for deadly diseases. Third, we learned that their populations grow exponentially, which we can model mathematically to predict infestations. Finally, our transmission risk equation proved that controlling the vector population is the absolute first line of defense in preventing global outbreaks. You now have a solid mathematical understanding of parasitic arthropoda.